Good afternoon. Welcome to Affinity Energy's webinar on reducing energy in industrial plants using equipment sequencing. So why are we here today? I often find in my travels and visiting manufacturing facilities and various other industrial facilities that oftentimes what might seem obvious and simple to me is something that's often overlooked when it comes to energy efficiency. So I'd like to share with you some control schemes that can be used within your plant to help you run your equipment more effectively and reduce your energy costs. So looking forward to sharing with you some knowledge that I've gained over the years, both as a control system integrator and as an M&V professional. So a little bit about Affinity Energy. So we're a specialty control systems integrator that specializes in mission-critical energy and distributed generation. That means that we have a firm understanding of how power is distributed, how energy is measured and controlled. Our specialty is really around SCADA systems, electrical power management systems, and programmable logic controllers. Additionally, we have expertise in submetering, which is often required in order to develop the KPIs that are needed to assess the effectiveness of the different control schemes and our different M&V plans. Lastly, we are a Schneider Electric critical power eco-expert, so consult with us if you have any needs that are related to critical power, whether it be emergency standby, power systems, or could be generation systems. Your manufacturing facility or your plant is a dynamic environment. It's constantly changing. So like everything, it needs to have the mechanism in place in order to address those changes. Now those changes can be production levels, it could be an expansion that's perhaps occurring within your facility and therefore you're adding more machines or additional processes. And as a result of that, oftentimes we find that the cost associated with various utilities, whether it be chilled water, steam, and compressed air, also increase as you expand and as the lifetime of a facility increases. And really what we want to do is be aware of this constant dynamic and come up with ways that we can address this constantly changing environment while providing the necessary resources to operate the facility, but also do it in an economic and environmentally friendly manner. What we're primarily talking about in this presentation are utilities such as chilled water, steam, compressed air. Those are the three primary utilities that I tend to see within an industrial facility. And one of the ones that I specifically see often overlooked is compressed air. And the reason for that is I find that a lot of the manufacturers that make boilers and chillers for producing steam and chilled water often have pre-developed control solutions that they can implement within a facility for managing the sequencing of chillers and boilers. But the compressed air industry and marketplace hasn't been as forthcoming with designs that incorporate equipment sequencing. So did you know that as much as 10% of energy use within an industrial facility is often allocated to the production of compressed air? And we do find that in some heavy industrial facilities that it can be as much as 30% of the electrical consumption. And to compound that, you'll find that with compressed air, it's a very inefficient process in which compressed air is generated. Typically, in order to generate air, say a 1 horsepower air motor to produce 100 psi of compressed air requires up to 7 to 8 electrical horsepower supplied. So you can see that it's not very efficient, and therefore the electrical consumption related to producing compressed air can add up to a significant expense within your facility. You know, when we talk about energy conservation and strategy, we often know that first and foremost we have to deliver the appropriate utility to the facility, the plant, or the process. That means meeting whatever the maximum output required in order to produce the comfort or to address the production levels within a facility. But we also want to do that in an environmentally and economical manner. So really we're talking about addressing the operational needs while reducing or minimizing the energy consumption. And most facilities typically will do this, and they'll address what I'll consider the low-hanging fruit. You know, they've oftentimes went through the necessary engineering studies to develop the correct set points, so knowing what pressures you might need to operate, what delta T in your chilled water system that you might need to maintain in order to maintain certain temperatures within your environment. Perhaps you've went through and done an audit and fixed whatever leaks that might exist, or other obvious energy wasters. Perhaps you need to make sure all of your pipes are insulated in terms of distributing steam or chilled water. Steam traps is another common energy waster within a facility. So certainly doing those maintenance and fixing what I call low-hanging fruit when it comes to loss of energy. And then also looking and eliminating what we call inappropriate uses. You know, I can say that I've been in many industrial facilities where compressed air is used in order to clean off the floors, which is a very expensive way in order to clean off the work environment. So again, looking for those ways in which the utilities may be used in an inappropriate manner is another kind of low-hanging fruit. But once you've kind of addressed those low-hanging fruits, really you're looking at an implementation that's going to involve a control system in terms of sequencing. It really comes down to understanding the equipment that you have in your facilities. And again, these are the equipment that are generating either the compressed air, the steam, or the chilled water. Just like your car, those pieces of equipment are designed to operate at an optimal set point. Just like your car might be able to travel the most miles, while traveling on the highway at 60 miles per hour, most chillers, boilers, and compressors are designed to output their utility at a design point which typically is near or close to the maximum output of the machine. So understanding this and understanding what the demand for that particular utility is in your facility is important, because we obviously want to operate those machines as close to the optimal set point as possible. So where do you run into a problem? Well, you run into a problem when the plant or the facility or the process requires a utility which needs to be serviced by more than one machine, and such that a machine has to be operated at what we call partial load. So for example, you may have a need for compressed air at a certain pressure and a certain cubic feet per minute, but that compressed air could be delivered by either two machines running at partial load, or maybe it's one machine running optimally. But again, those are decisions that should be built in or thought of up front and require intent in your design. So in order to really implement a proper control sequence for equipment sequencing, it really does require understanding something about your facility in terms of its demand or its production levels. Each machine that you typically have can have, you can order it from the OEM with different capacity. And that means, again, that it's designed to deliver a certain amount of its utility, whether it be chilled water or whether it be steam or whether it be air at a certain pressure and certain flow rate. And once you understand the full range of your production or your demand levels, meaning how much of the time do I operate at these different set points within your facility, it allows you to kind of look at the design in terms of selecting the machines. What I typically find is that within new facilities, going through this process of understanding the demand and the load levels such that you can size the capacity of your different utility or resources within your facility is often commonplace today. But where we run into a problem is certainly in the retrofit environment. And part of that is due to a little bit of the challenge associated with implementing equipment sequencing within an older facility. The strategy, in theory, is pretty simple, but it does require intention, and it does also require instrumentation in order to implement. And this is one of the challenges associated with retrofit. A lot of the older machines and a lot of the instruments that were installed in older plants do not have the capability to measure both the output as well as some of the process variables and the inputs that would be required in order to measure and track the effectiveness of an equipment sequencing control. So let's talk a little bit about implementation. So when we talk about implementation, there's a couple considerations that we need to pay attention to. The first is talking about sizing and resolution. So if you're in an existing facility, you may not have the ability to necessarily size their existing equipment. You may be stuck with what you currently have, so you have to take a different approach in terms of looking at your control sequence. Whereas if you are in the design or you're developing a facility, you have the opportunity up front to determine the size and the resolution associated with your machines. So for example, let's say that you have a facility that requires 5,000 tons of chilled water. Well, there's a couple different methods that you can go about designing or specifying the capacity of your chillers. One strategy may be to use 3 2,000-ton chillers, again allowing you to have a little bit of reserve or capacity for the future, but again understanding that ideally you'll run 2 of the chillers at full capacity or near capacity, and 1 of the chillers you'll typically run at 50% capacity. So again, it'll be the machine that ideally runs at partial load, as opposed to, perhaps one approach might be, you could size the second strategy would be I install 2 2,000-ton chillers and 1 1,000-ton chiller, which would ideally allow you to address the current needs for your 5,000 tons of chilled water. However, in the future, it may not allow you to expand without adding another machine. The other thing would be, for example, that anything less than 5,000, you are going to run at partial load. But another nice thing that you have with having a smaller chiller, which could be considered your trim chiller, is that when you run at 3,000 or maybe even run at 1,000 tons, so let's say you're running during the winter or the fall or early spring, you may be able to address partial load conditions in a more cost-effective manner. And there are considerations. When you have more machines, you take up more space and you require more complexity in terms of the piping and potentially the instrumentation that's required to measure things such as flow rates and temperatures, etc. Another consideration when designing your equipment sequencing controls is to really understand the variability. If your process is fairly consistent, and again, this might be the difference between a process environment or a manufacturing environment versus, say, a commercial building or a hospital or an institutional environment, then it may be that you can use what we would consider fixed output machines. But something that has become more popular within the last 5 to 10 years has been having variable speed chillers, variable speed compressors, and also even boilers that can operate at different levels or have different outputs. Now, using a variable speed machine can also introduce other considerations. It's higher capital costs. There could be increased maintenance in terms of dealing with that type of machine, and also perhaps personnel training in terms of working with that technology, which tends to be a newer technology. But the advantage of a variable speed machine is that it can actually be efficient in terms of being your trim machine or being the machine that needs to address the partial load condition. So again, it's something that is available in today's industry, and depending on your environment and how much your load varies, again, understanding how often you spend at the different load levels might allow you to utilize this technology in terms of addressing the operational needs, but still minimizing the expense in terms of energy consumed. Earlier in the discussion, I talked a little bit about the need for instrumentation, and specifically for metering. And the metering can be electrical metering. It may also be metering for measuring, in the case of a chiller, BTU, because BTUs is measured by understanding the supply and return temperatures as well as the flow rate of the chilled water being delivered to the load. It may be measuring pressure at the end of the line. So again, if you are trying to maintain a set point for your compressed air, you may need to measure the pressure at the furthest point within your system. But again, all of these, in order to implement a equipment sequencing control scheme, it does require that, again, the various input and output parameters be measured in real time, because your control scheme, and whether that be through your programmable logic controller or through your DDC system, is going to have to make decisions on which machines to sequence on and off based on real-time measurements that are coming from not only installed instruments but calibrated equipment. So important to make sure that, when you put in a control sequence that's going to require the measurement of input and output parameters, that instrument is also calibrated on a regular basis. Just going back to that, for example, one of the things that we often find when it comes to steam production is it's good to understand the amount of fuel, because the fuel for producing steam could be either natural gas or it could be fuel oil. And by knowing the input, again, you need to understand at the end of the day the cost for producing that utility, and therefore without measuring the fuel consumption, whether it be natural gas or fuel oil, you'll have a hard time quantifying and determining how to configure and how to prioritize your control scheme in the absence of that measurement. So one of the other topics that often comes up when we discuss equipment sequencing is the determination within your control sequence of when to sequence on a new machine. So for example, let's say that you're currently running your plant, and during second shift they call for greater production levels, which is going to require either more compressed air or it may require more steam. At some point in time, you will have to cycle on a second machine. And the set points at which you transition from 1 to 2, 2 to 3, or 3 to 4 is typically predetermined within your control sequence. And not only the set points at which you make that transition, but there's typically a priority. So, if you've got 3 or 4 machines, you typically have one machine, which is obviously the first machine to come on, a second machine, that would be the second machine to come on, and typically that priority might be determined based on operational run-times or some other methodology that you might implement. Perhaps you want to equally, you want to load up, or you want to use your machines and try to balance out the run times. So therefore, you might have a control sequence or perhaps a procedure that, maybe for certain months of the year, machine number 1 is first priority. During other months of the year, machine number 2 is first priority. But that allows the machines to carry the load or to operate in a fairly balanced method. Some other strategies that are used are they don't worry about balancing the load. They will put most of the load on a single machine, and then at some point in time when it reaches a designated point, they'll actually then reprioritize, and maybe they'll do the maintenance or an overhaul on that machine, and then they'll change that machine's priority such that it'll be second or third or maybe last priority. So again, it really just depends on your environment and your strategy in terms of how you go about operating your environment. But getting back to determining the set point at which you transition or cycle on a second or third machine, one of the things that needs to be accounted for within your control scheme is what we call hysteresis. So hysteresis allows you to avoid excessive cycling of equipment. So for example, let's say that you're currently operating and you need 200 tons of chilled water. The process requires 300 tons of chilled water. At a certain point in time, you're going to have to add that second chiller. So you can see here, moving from left to right is time, and then the set point at which you would add that second chiller is shown by the solid line on the top graph. Now, once that second chiller is cycled on, it's going to operate for a point in time, but you'll notice that the arrow in red, which would be the point at which the load falls down below the set point at which that second chiller came on, at that particular point in time, we aren't going to turn the second chiller off. We're going to force the load to drop back to a level which is shown by the dash line in the top graph. And the reason we're going to do that is, again, if we were to turn that chiller on and off at a discrete point, set point, what could potentially happen is, as the load, if it were to vary around that particular solid line, we would end up what would be called excessive cycling, where that chiller would want to turn off and on in a manner which would be harmful to that equipment. It could reduce the lifetime of that equipment. So certainly we want to be cognizant of, when we do our designs, to include hysteresis. So again, you'll see the chart below kind of just tracks the number of machines that are active based on the load that is on the facility. So now that I've kind of covered a couple of the implementation considerations when it comes to equipment sequencing, I want to talk a little bit about a practical application. And this was some work that Affinity Energy did for a fiberglass manufacturer. When I talk about fiberglass, I talk about fiberglass insulation in the home. So we had been working with one of the major OEMs of fiberglass, and they had a centralized air compressor room in which they had multiple machines that provided compressed air to their process. They had pneumatic controls, and then they had other things within their process that required compressed air. And those compressors, initially when we got involved with this particular manufacturer, were run on a schedule. So they knew that, during certain times of the year or even certain days of the month, that certain compressors were going to run based on production levels or, whatever was occurring within the facility. There was no mechanism for measuring the amount of energy being consumed by the compressed air system, and there really wasn't anything in the system in terms of matching the compressed air generation to the load required. Additionally, we found that within the facility there were a lot of instances where inappropriate uses of compressed air were taking place. So over a period of time, and it was a phased implementation. The first phase was to get a better idea and measure the specific power that was being used by the compressed air system. So electrical submeters were installed in the vicinity of the switchboards that were providing power to the air compressors, and this power was then recorded to a plant historian, which then could be matched up with the compressors that were running. Additionally, the pressure within the compressed air system was also recorded in the plant historian. And then based on that, looking at the cost of energy, the cost of electricity, as well as the specific power by the compressed air system, the owner was able to benchmark the energy use for compressed air. And what they found is that compared to industry standards in terms of specific power for compressed air, that they were in excess of what the typical industry was consuming in terms of energy use. So the next step was to then upgrade the controls on the compressor. So again, this was a retrofit environment, and so as you can imagine, or based on my previous comments, being able to implement a equipment sequencing control scheme was not straightforward, because it did require, again, number one, we had to measure the inputs and the outputs, and then we also had to tie a cost to that in order to then prioritize. Additionally, the control panels needed to be upgraded, and then ultimately a control sequence needed to be implemented. We were able to reduce the compressed air energy expense by 15%, which represented $150,000 a year, which again was a significant expense that was automatically now could be utilized for other initiatives within the plant. So like most energy savings or energy conservation measures, the nice thing about reducing utility consumption is it affects the bottom line immediately. And not only that, there's a year-over-year effect. So moving forward, the savings is achieved year over year. Now, and they're left with a tool that allows them to ensure and continue to assess this efficient operation of the compressed air system. And not only that, as the plant expands or contracts, they can make modifications so they can ensure that their energy intensity is in line with their energy expense for compressed air. In conclusion, one of the things I do want to state, understanding that equipment sequencing in theory is simple. The idea that we try to run as many machines at their optimal levels to address the specifics of the process or the facility in terms of its utility needs, while minimizing the amount of machines that need to run, such that we only run one machine at a partial load condition. I mean, that's really, in a nutshell, the idea behind equipment sequencing, but also taking into account that part of your design has to be, best practices related to determining the set points at which you would transition or cycle on a new machine, as well as cycle off a new machine, and also the procedures around prioritizing how you accumulate runtime on those machines to, again, not only take into account addressing the load with the appropriate capacity, but also minimizing the energy or the impact in the environment, and also maximizing the lifetime of the equipment. Ideally, a successful control sequence implementation helps an owner to address all the needs that they require, so it takes a holistic view. But again, there's plenty of opportunity based on the experience that we've seen going into older industrial and manufacturing facilities, but it does require an investment. Like most things in life, there's in order to get a payback is going to require an investment, and Affinity Energy has helped owners, whether it be in industrial facilities, whether it be in central energy plants at hospitals, or even data centers, in order to implement control strategies that help address the operational needs while minimizing the energy consumption. So that concludes our webinar today. I hope you've been able to take away some best practices and recommendations in terms of implementing an equipment sequencing strategy that will help you address not only your operational needs, but maybe extend the lifetime of your equipment and operate your equipment in a cost-effective and economical manner. Thank you, and I look forward to talking to you soon.